Hello everyone, today I will present my final project, the persistent homology of neural network activations, a layer-wise analysis on quick draw dataset. So for the introduction, the neural networks are powerful but notoriously difficult to interpret. While accuracy and loss are standard metrics, they don't tell us much about what transformations happen inside the network. Recent work has proposed a new lens, topology, to study how neural networks process data. The core idea is that neural networks simplify the topological structure of data as it flows through the layers. For example, if the input has multiple connected components or loops, this should disappear in deeper layers. Understanding this transformation helps us grasp how neural networks compress information and make decisions. Our project builds on the 2020 paper Topology of Deep Neural Networks by Knight, published in the Journal of Machine Learning Research. In that study, the authors examined the persistent homology of various neural network architectures and drew conclusions about how activation functions, network depth, and width affect topological simplification. Our motivation was two. First, we replicate the MLP settings of the original study on real-world dataset, and secondly, we extend the work by incorporating convolutional layers. So this is our methodology part. We choose the quick draw dataset as our training data. So we can see that it consists of like many categories of people's hand draws. So here is an example of the bottle cap. Although like different people draw the bottle cap differently, but we can still see that there's a common feature. For example, they usually all have a circle shape in drawings. So this dataset is an ideal candidate for exploring how neural architectures adapt to richer visual semantics and whether topology can capture this process. So for our neural network architecture, we chooses the MLP and the CNN as our model. So the MLP consists of 10 fully connected layers, each with 10 neurons using the Leakey-Relu activation function. So this mirrors the architecture used in the original paper. For the CNN, we designed like two convolutional layer plus 3 dense layers structure. Like for example, we can so this picture here shows that there's two convolutional layer, and each layer consists of a convolutional layer, activation layer, and a max pooling layer. And we also use 3 times 3 kernel size to extract the feature. And yeah, these are the 3 dense layers, and finally we will have a like a logits to be classified. So this allows us to investigate whether convolutional layers induce different topological effects than fully connected layers. For each selected layer, we extract the activation outputs and treat them as point clouds. However, point clouds are not topological spaces by themselves, so we construct a VR complex which connects points based on pairwise distances. The key idea is that a k simplex is added whenever k plus 1 points are mutually within a distance epsilon. So here's an example. Um, so as the epsilon increase, so we can say from 0.15 to 0.4 to 0.6, um, the points are gradually connected to form edge and form triangle shapes, and even some higher dimensional simplexes to form a topological space. Rather than choosing a fixed epsilon, we compute persistent homology by sweeping over a range of epsilon values. This results in a filtration, a nested sequence of simplicial complexes that grows as epsilon increases. Topological features appear and later disappear as new simplices are added. The lifespan of a feature is quantifies its persistence. Features that persist over a wide range of epsilon are considered robust and likely to represent meaningful structure, while short-lived features are usually interpreted as noise. So here comes our experiment part. For the setup, we choose two categories from the quick draw dataset, which are the BERT and the BOTOCAP. We choose two neural networks, the MLP and the CNN, and we do three visualizations: the barcode diagram, the persistent diagram, and the scatter plot. And we use the topological complexity to be our evaluation metrics to like represent the topological structure within each layer. So it is defined by the sum of Betti numbers within each layer in the paper. So here is our result. These two pictures are the left picture is from our MLP neural network, and the right picture is from CNN. So we can see that at the very first stage of both neural networks, there are a lot of like red bars and blue bars, which represents the connected components and loop structures in the like high dimensional space. And we can see from the scatter plot that the two classes are not separable since the points are gathered together. But as our network goes deeper, we can see that the number of bars gradually decrease, and even at the last part of the network, the blue bars got nearly vanished, which means like the loop structure nearly vanish. And from the scatter plot, we can see that the two classes can be linearly separable. So this finding verifies the key findings in the paper, that is there is a consistent reduction in topological complexity across layers. And here is the Betti number comparison plot for our MLP and CNN. We can observe that the first layer of the CNN exhibits significantly higher topological complexity than that of MLP. This can be attributed to the CNN's convolutional nature, which retains rich local spatial structures in early layers. And we can also see that the CNN drops more rapidly than the MLP. So for the limitations, due to the computational cost, we restricted the number of layers and data samples. Additionally, we didn't perform rigorous statistical comparisons across multiple training runs, which limits the generality of our findings. We also focused on supervised classification, the role of topological simplification in other learning paradigms remain unexplored. So in the future, we want to address these issues by scaling to larger dataset or examine different network architecture and tasks. Thank you.